those pictures in front of you. So there are different variations of a normal curve, but they all have a similar bell kind of shape. Some of them are taller and spikier, some of them are spread out more. Just kind of depends on the scale that you view them on. This is a normal curve. When it has a scale like this at the bottom where 0 is in the middle, and then it's scaled by units of 1, this version right here is called a standard normal curve. Okay. And the thing that makes it a standard normal is the scale. Okay. So we're going to turn it into a different normal curve by just playing around with another measurement that we could take. So IQ scores aren't as popular as they used to be, which is a good thing. But IQ scores are said to have an average. The average always goes in the middle, right? The mean of 100. And a standard deviation of 20. So what IQ score would be one standard deviation to the right? 120. And then one standard deviation, or two standard deviations to the right. 40. And then 3 standard deviations to the right. All right, so it's pretty easy. We can just count over. And in the middle is exactly 100. Oops, extra pen mark. And then we can also go the other way. This guy. So if we go the other way, one standard deviation to the left would be 80, 2 standard deviations to the left would be 60, and 3 standard deviations to the left would be 40. Okay. So we played around with percentages. What's up? That makes a mistake?
No, 110 or
that's 100 in the middle. Sorry, my 0 didn't come out very good.
I was just making.
That's a 0 right there. So I've scaled this in 2 different ways. So what number is 2 standard deviations to the right?
140.
140, right? So notice that there is a 2 right here. So when you count by standard deviations, that's called a z-score. Notice they put a z here on this particular picture. So just a note, those black numbers there, those are called z-scores. And all a z-score is it just counts standard deviations. So a lot of times when you do standardized tests, they'll give you back information like what was the average of the standardized test, what's the standard deviation of the standardized test, what was your percentile rank? I'll talk about that again in a minute. That's kind of like, the 75th quartile, the 3rd quartile or 75th percentile. Oftentimes, though, you'll also be given a z-score. And a z-score just means how many standard deviations is your score above average. Okay? So suppose somebody had suppose somebody had an IQ score of 150. How many standard deviations to the right of the middle is 150?
2.5.
It's 2.5, right? So we can just kind of see that, right? So how would we actually calculate that? Like you guys can, what if it was a different number? Like suppose I said it was 127, right? Then it wouldn't be as obvious what it was. We know it's somewhere between 1 and 2 standard deviations. So what would we do to calculate that 2.5 you just told me?
Isn't it x minus the mean?
Yeah, so we have to find the deviation. Yeah, so what's the deviation of 150? Well, we would just take 150 and we would subtract 100 from it, right? And that's going to give us 50. Okay, so it's 50 to the right. What are we measuring by here? 20s. Yeah, how many 20s are in 50, right? So that's just division. So we just divide by the standard deviation, and that gives us that 2.5. You guys just looked at it and saw it, right? So one way to think about a z-score is it's just counting how many standard deviations a score is above or below average. We can calculate it by finding the deviation and dividing by the standard deviation. So that's another way to think about a z-score. Z-score is what Kristen said, it's the deviation, which is whatever measurement we're looking at. And here was the measurement of 150 minus the mean divided by the standard deviation. So that's how we calculate it. Deviation, which is how far you are to the left or the right, divided by what a standard deviation is in that situation. And every situation has a different standard deviation, every data set. All right, so I threw some percentages out that normal distributions always follow. So I'm going to take another picture of this graph, bring it into a new window because it's getting kind of messy here. So does anybody remember what's the percentage that goes with one standard deviation to the right or the left? What percentage of scores are within one standard deviation?
Isn't it like 68?
68%, yeah. So if I draw a vertical line up from the negative one and up from the positive one, 68% have to live in that region right there. Within 2 standard deviations, so that would be from here all the way over to there. What percent lives within 2 standard deviations?
95.
Yeah, that one was about 95%. And then within 3 standard deviations is almost everybody.
Like 98.8.
Yeah, so sometimes that was one of our examples. Some people call it 99, some people call it 99.5. More accurately, it's like 99.7. Let's just call it 99 for today. We're going to say it's about 99%. Actually, a little closer to 100% within 3 standard deviations. Okay. So I've got a mission for you right now. There are, let's see, there's a little tiny vertical line right there, another one right there. So I have 1, 2, 3, 4, 5, 6, 7 vertical lines here, and they chop this. This is a histogram basically. They chop this histogram into 1, 2, 3, 4, 5, 6, 7, 8 regions. What percent of scores would be in each of these regions?
It's like 12.5.
What's that?
Like
So-
12.5%.
Well, everyone's going to be different, right? Because
Oh, yeah.
basically these are like stacks of people right there, right? So let's do the easiest one to do is, let's say, this one right here. What percent have to be in that region right there?
34.
Yeah, because there's 68 and the 2 pieces combined, the mirror images. So that region right there has to be 34. Oops, not a pen. So I want you to try and figure out, check with your neighbors, do a little arithmetic. We just nailed 2 of them. There are 34% in this region. There are 34% in that region. It's got to be less than 34 in these 2 regions on each side there. So play around with a little math, a little problem solving. Come up with the percentage in each of these other regions. There's enough information to pull those out. Anyone get the percent between 1 and 2 standard deviations? 13.5. And that'll be the same on this side because we have symmetry. Anyone get the one between 2 and 3 standard deviations? 2%? Yep. And then how much in the little skinny tail on the side?
That would be 1%.
Almost, the tails have to share 1%.
What part?
So it'd be 0.5%, yeah. So this would be 0.5%, or you could call it 0.5%. Live out on that tail there. And then again, there'd be 2% right there.
How did you get that? All of that?
Somebody want to explain how we got one of those other numbers?
So 68 takes up a big chunk in the middle, so 95 is taking up all, like 68 and the 2 extras. So you take 95 minus 68, and then you have 2 sections that you need to find. So you divide that by 2. They're equal. They're right there.
Yeah, so if you take away the 68% from the 95, that's what lives in these blue areas here. So 95 minus 68 is 27. So that 27 has to be shared in these 2 regions of the histogram.
It's the same process to find the next one, which is 99. Take away 95 because you already found 68 and the 95% ones. So that's 4. And you divide that by 2 because there's 2 equal regions.
That kind of make sense?
Yeah.
Yeah, and for me, I got to kind of draw it out to see that happening. So there's 95% from here all the way over in this whole thing. If I cut the 68% out, that means these 2 chunks right here and right here have to split that 27. That got nice and messy, didn't it? All right, so I'm going to bring this into another window so it's not so messy. And we're going to answer a couple of questions based on it. What's that?
And coordinate, she's going to look at it and go.
All right, let's make this bigger. All right, so just what did we calculate? So we calculated this is 34% there, 34% there, 13.5% here, 2% there, and 0.5% that lives in this little tiny skinny tail out on that side. Similarly, on this side, there's going to be the 34, 13.5, and 2, and 0.5% up there. So if we go back to, let's see, we were playing with human body temperature yesterday, and my claim was that the middle of human body temperature right there was 98.7, because that's what we believe it to be in Fahrenheit. And some research I looked up says standard deviation is about 7.7 of a degree. So this is our mean. Standard deviation for human body temperature is about 0.7 degrees Fahrenheit. So for example, 1 standard deviation to the right would put us at what, 99.4? And 1 to the left would put us at 98 degrees. Okay. So what percent of people, if I randomly grab a person and I take their temperature, what's the chance that they'll have a temperature below 98%? So probability that their temperature is less than 98%. Sorry, that's supposed to be 98 degrees.
Is it going to be less than or equal to, or exactly less?
Okay, so since like there's infinitely many temperatures somebody can have, whether it's equal to or not is irrelevant when we do normal distributions. Yeah, so it wouldn't matter. It wouldn't change the answer if I put an equal to there.
Okay, so it would be 16. What, 16?
Yeah, so we got 13.5 plus 0.5 is 14 plus another 2%. The answer would be about 16% chance of that happening, of finding a person with a body temperature less than 98 degrees.
So you include that 98 no matter what.
It doesn't matter whether you include it or not. So even if I rephrased it like I did the first time and I just said less than, the answer is still about 16%. Yeah, so if we know a given population of data is normally distributed, then we can just use these general ideas about the normal curve to answer questions. So they're just kind of rule of thumb thing. How do I know if a data set or a set of measurements is normal? So, big question. We're getting used to what a normal distribution is. Is a data set normal? Question. How do you answer that question? It's a hard question to answer. One thing we look for is we want the histograms, I should say, grams, there we go, to be symmetric bell shapes. Now, there's a ton of different symmetric bell-shaped curves out there. Some of them are normal, some of them aren't. Okay. So the next thing we look for are those standard percentages. And so what are the standard percents? That within one standard deviation, we'll see about 68% of the data.
Is that always going to be the same?
The 68%? If it's normal, right? And there's lots of data sets that just ain't normal. And we'll look at a couple of examples of that. B, if we look within 2 standard deviations, we would expect to find about 95% of the data. And within 3 standard deviations, we would expect to find about 99% of the data. And counting those percentages is a good amount of work. I mean, you got to find those measurements, then you got to look at the data and count up how many are in between those markers. And making a histogram can help do that. So if the histogram isn't bell-shaped, usually we just say, yeah, it's not normal, and we're done. If the histogram is bell-shaped, then we look at these percentages and see if the data matches up with these percentages. If all of this works, does that mean the data is normal? Maybe. There's still no guarantee because we're only looking at one data set. There's lots of other possible samples one can take. Okay. So it's not a sure thing. It's kind of a fuzzy little science there about determining if a certain measurement kind of thing is normally distributed or not. It usually takes lots of studies to kind of figure that out. So you will see normal distributions a lot in research, in test results. But it's just, you want to be careful. It's not safe to assume everything is normal. If you take more statistics in the future, you'll see some other reasons why we think a normal distribution is so important, and it really is important in mathematics. But those ideas are related to more about making predictions than they are to describing data. So when you take a statistics course, after you do the descriptive stuff, which we've been working on for the last 3 weeks, then you jump into trying to make predictions, which is called inferential statistics. And it's really cool stuff. It's just a different kind of math. All right. So we've played with something like this before, sorta. Let's go back to our home page. I think it was the hours of TV per day, or was it the movie one? Let's take a look. Okay, so here is one of our samples. This was the number of hours people spent watching TV, and there was a problem with this data set here because people said they watched like 40 hours of TV a day, which clearly they didn't understand the question. So this was before I scrubbed it. Somewhere I have a better one. There we go. Okay, so this one right here is one we made where we made those human readable bins that most people like to see. Is this a bell shape? Definitely not a bell shape, right? So somebody might say, well, it's not a bell shape, but it might be normally distributed. So we can check that out by just making a couple of calculations. So here's my data on the side there. And you're going to do a similar kind of thing when you're playing around with your take-home exam. So I'm just going to sneak this out. put it in a new tab. And with standard deviation. Paste that in there. So I'm going to calculate the mean here. Anybody remember how to do the mean on a spreadsheet? Equals average. Nice, yeah. And do we want the average or the average A? Usually average, yeah. And then we just select the data. There's nothing else in the column, so I can just select the whole column. Okay, so it says the average number of movies from the people I surveyed was about hours of TV a day. 2 hours of TV a day. All right, let's see what the standard deviation is. So equal, start typing ST for standard, and it'll give you a bunch of different options. We're going to use pretty much the STDEV. If you take a statistics course, you'll get an explanation about the difference between all the various kinds of standard deviation are. And it's really straightforward. Just select the data again, and the computer says, the standard deviation is about 2. Right? So let's draw a number line. So let's call it 2.4, and let's just round that one down to 2. And there you are. Hours of TV per day. We're going to call the mean 2.4, and we'll call the standard deviation 2. So if I put that 2.4 in the middle, and I look 1 standard deviation to the right, where's that going to put me?
4.4.
Going to put me at 4.4. That would be a z-score of 1, right? Because it's 1 standard deviation to the right. Okay, so remember, z-score just counts standard deviations. If I go 1 standard deviation to the left, what's that going to put me at? 0.4. Right? So let's look at the data that I just had and see how many numbers are between 0.4 and 4.4. So I go back to my sheet here, and are these sorted? Looks like it. All right, so 0.5 is in there, right? All the way down to 4. So 21 minus 1 is 20 out of 24 numbers. So within 1 standard deviation, I've got 20 out of 24 of the numbers are within there. Anybody with a calculator, what's 20 divided by 24?
It's like 5, 6.
83.
About 83%. If it was normal, what would we expect to see? 68%. So not only, I mean, it doesn't look normal, and the percentages don't match up either, right? Other times the histograms can look pretty normal, but the percentages won't match up. I mean, it's just the way it goes. There's all kinds of different shapes when you make histograms.
So if you had a normal within 1 deviation,
Yeah.
and then on the histogram it looked like the next 2 were normal, but they were off by like points.
Yeah, so then it's like, hey, this might be normal. I don't know. We'd have to do more studies and see if the next study looked normal too. Yeah, and it's something that over time evolves to say, hey, this kind of measurement seems like it's normally distributed. And there's many kinds of distributions out there. Some of them have names, but there's infinitely many shapes that don't have names. You know, and that's just the way it is. So the big points here are some data is normally distributed. Normal distributions are very powerful if you take later statistics for predicting things. Like, for example, a lot of times you, like during presidential elections or others, you get called up and saying, hey, who are you going to vote for? And they want to know information about you. Often they'll say, are you female in this age range and non-white? Answer no, they hang up on you. They didn't want to talk to you. They want some other kind of person. But people do research and try to predict who's going to win the election. How do they do that? They don't sample everybody, do they? How many people should they ask to get a good prediction of the result? And part of that, how many people should they interview, is related to normal distributions. And it's really fascinating stuff. Other things that were important here is deviation is an idea of how far somebody is from a mean, and that's often used when reporting standardized test scores.
Sorry, that was my husband.
It's your husband?
Yeah, he wants to know.
He wants to know if you heard of that.
Yeah.
So you will see the idea of z-scores, and z-score is just a really simple idea. What's a z-score again? It's just a count of standard deviations. How many standard deviations is some measurement from the middle? That's all it is.
And it would be like 0, 1, 2, 3.
Yeah, so it could be like 1.1 or 2.2, but it's very rare to see a z-score above 3. But there are some distributions that are pretty spread out. So I've seen data where you're going to get a z-score of 10, which seems crazy, but it was in a kind of measurement that just wasn't normally distributed. Okay? It's still very rare, and there's other rules about how far out things are going to reasonably be in a population. But typically z-scores will be some number between -3 and 3. That's what we'll typically see, whether the population was normally distributed or not. And again, it's just a measure of, on average, how far is something spread out. Okay. All right. So the next thing I want to look at is a weighted average. And for that one, I want to reflect back on the playing with data from movies. And the spreadsheet. Maybe. Hello, did I click that or not? There it goes. All right, so let's see. I want movies seen in a theater because those numbers are more reasonable. So let's copy that into a new sheet, I think. Let's just make a whole copy of it. New copy. It's not a good name. Don't follow my lead there, Kristen. Nothing.
I wasn't listening to you. You're mumbling.
Okay, so I'm going to sort the data here. So data, sort range, has a header row, smallest to largest. Okay, so I have 39 measurements here because there's a title on there. So I'm going to create a, what do we call it, a frequency distribution table. So for that, I need to have my buckets or bins. Oops. Close. All right. And we got 0, 1, all the way up to something like 4, maybe. Yep, 4 is the max there. And then we're going to make the frequency count. All right, so can somebody help me remember how to do frequency on a spreadsheet?
You go down one past the count.
So highlight 1 past the buckets, yep.
And then hit equals.
Yep.
Then start typing frequency. Hit frequency.
Okay.
And then copy your data.
Okay.
And comma. And then copy your bin.
Okay.
For your buckets.
Bin, buckets, classes, yep,
And then
something
close
like
it.
that. Close it and enter. Yeah, for Excel users, do you remember the secret instead of hitting enter?
Control or something.
I think
like
it's shift enter.
Shift enter.
Yeah, and you'll figure out you made a mistake because in Excel, if you hit enter, you get one number. And you got to do it all over again. So it's frustrating. Okay, so rather than having to look at all of the data, I could just look at this snapshot of the data. And we do the extra one just in case there's something above the highest one I missed. And we miss things. We all make mistakes. So let's just clean this up a touch. Let's see, we'll center it and zoom in. So let's suppose this was all we had to go by. We didn't have the whole data set. Frequency. What I want to do is I want to figure out what is the mean for this data just based on the frequency table. Okay. And this is the idea of a weighted average. So I'm going to copy this into my workbook, and we'll do it together, and then we'll do it on the spreadsheet. Let's see, I want screenshot. Where are you? There you are. So if if I didn't have the frequency column there, it would look like somebody watched no movies, and somebody else watched 1 movie, and somebody else watched 2 movies, and somebody else watched 3, and somebody else watched 4. That's 1, 2, 3, 4, 5 people. Divide by 5, and that's my average, right? But that's not the case here, right? How many people watch no movies?
17.
Yeah. So what I have to do is I have to adjust the number of movies people watch by how many people watch them, and that's called the weight. So 0 has a weight of 17. 17 people watch no movies. And then squeeze in a little space here. How many people watched 1 movie? That is 10 of them. So plus 10 people watched 1. How many watched 2? 7. So then I squeeze in 7 times 2 there. And 3 times 3 is the weight. And for the 4, there's 2 of them, so 2 times 4. I know it looks kind of messy. So cleaning that up a little bit, I've got, what, 17 times 0 is 0, and 10 times 1 is 10, and 14, and 9, and I can't quite fit. And then 8 more. Now, instead of 5, that's not quite right. I have to add up all of the frequencies. And what should those frequencies add up to based on what we saw earlier?
38.
I think it was 39 they should
But
add
you
up
had
to.
a label.
I think there were 40 rows, let's see. But we can add those just to double check. Yeah, it ended in the 40th one. Yeah, so and it's always a good idea to double check by doing a sum on that, right? So off to the side here, I could do a sum and say, please add up all of the frequencies. And yep, computer says they do add to 39. So then we just divide by 39. So what does that give me? 10, 20,
So you wouldn't add the 5 and
41. What's that?
You wouldn't add the 5.
No, the 5 was me misreading the graph. Because there were 1, 2, 3, 4, 5 rows there. Okay, so that was just me doing bad math. The bottom line is an average is divided by how many numbers you have. And according to the frequency, we have a count n equals 39. We always divide by the count. Okay. Yeah, so what do we get? That adds up to what? 10, 20, 30, 41? Is that right? So that's 41 out of 39, which is a little over 1. So 1 point something. Anybody, what is it?
05.
05, okay. So on average, this group of people watched about 1 movie, what is this data again? Movies in the theater per month is this one, yeah. So on average, these people watched about 1 movie in the theater a month, right, for this particular data set. And that's all the weighted averages. Each number that you're looking at occurs a certain amount of time, so you have to consider those weights when you add stuff up. So another version of a weighted average.
How is that different from average?
It's different from average. No, it's not a stupid question. It is an average, but if I only have the frequency table, I don't have all of the numbers. So so if I want to do a straight average on this, I would have to write down 17 zeros, and then I would have to write down 10 ones, and then I would have to write down 7 twos, and then 3 threes and 4 twos. Right? Because an average is add up all the numbers. So the weighted average is just one way to add up a different way to add up all the numbers.
Oh, but it's
That's
the
all.
same answer.
It's the same answer. Yeah. This is the weighted average is the average.